thanks for the introduction. Welcome everyone. My name is Liz Makeley and I'm the Product Line Applications Engineer here at Keithley. I support DMM's DAX, switching and sensitive product lines, and I also specialize in automotive and battery test solutions. Today I'll be discussing some safety considerations for battery testing and how to best protect your test equipment. So what are we going to cover today? We will start on a discussion on why safety is an important consideration when testing batteries. We'll go through factors that may introduce safety risks and ways to mitigate those risks to prevent a failure. And then we'll move on to some mechanisms to protect your test equipment in the event of a failure. So we will go ahead and get started. Batteries are considered unlimited power sources. Sadly, this doesn't mean that we get unlimited power from them, but rather that the output of these sources is not limited by internal impedance. So things that are generating current, like batteries and solar panels, fall into this category, especially when they're in a configuration that's large enough to generate significant current, like a battery pack for an electric vehicle. Another example that we all have in our houses is line voltage that comes out of the wall outlet. And that's why we've got those gray fuse boxes in our houses to prevent any dangerous current draw. Most common power sources, like a DC power supply that you'd have on your test bench, has internal mechanisms to limit the current. So even if you short that power supply, you're never going to get an increasing current. It'll be stopped at a certain set limit. And this can be done through a set resistance or with a more complex circuit that uses some FETs that gives you flexibility. When we talk about safety and test equipment protection, I think that most everyone knows that high current is very damaging. And with unlimited power sources or low impedance power sources, they can produce a very large current very quickly if they end up shorted. But we also have risks from exposure to high voltage, which doesn't necessarily have to exist with high current. For example, you can have a high current and low voltage when you have the output of several parallel battery cells shorted. And open circuit on several series configured battery cells gives us high voltage but no current. High current occurs in the circuit when we have a low impedance state like a short, and depending on the levels of current present and the path of the short, failures can be small, like just a single device burning out, but they can also be really catastrophic. High voltage typically occurs when something isn't grounded properly or a circuit suddenly becomes open. High voltage can cause devices to break down, especially devices that are supposed to be insulating, and they become more conductive. This process generates heat, and that can compound the effect of the current increase and damage nearby devices. A worst-case scenario is an electric arc, where the energy output is so large that the air breaks down and forms a conductive plasma. This plasma has essentially no resistance, so that current is allowed to flow freely. The danger of the arc is the intense heat that's produced, which leads to lots of damage and fires. Typically, when we see a board that's been damaged to the point of melting, it's because there was an arc present. Hopefully this goes without saying, but we'd really like to prevent situations where high current and high voltage can cause damage. When a situation goes awry, the device or the test equipment can get damaged, and that means increased cost to replace the devices, buy new test equipment, or repair the system as needed. In a manufacturing situation, this could be even worse because then we end up having to wait for a repair or a replacement, which means a line down situation on our test system. And even worse case than that is that an operator could be injured, either from electrical shock or from a fire resulting from an arc. So even though a lot of our discussion is focused on ways to prevent damage to test equipment and the devices while testing, all of these improvements are crucial for operator safety as well, as they reduce the chances of accidental shock or fire. So obviously, it would be great if we could just always test devices and signal levels that don't cause any risk of harm. But it's just not possible with the way that our power needs are going. A battery pack that's only capable of outputting 40 volts and 10 milliamps would be safe to grab barehanded, but that doesn't give us any distance in our cars. So if we know that we're going to be working with devices and levels that could potentially damage our equipment or cause operator injury, we need to consider factors in the test setup design that can help reduce the risk of failure. The first question you should be asking is, what's the limit of my test equipment? Along that same line, anything that goes in between your measurement instrument and your device needs to be properly rated. Identify places where connections are being made between wires and devices. These are points where the conducting elements could be exposed, and that would increase risks of shorts and shocks. Examine your circuit and identify the largest signals that would be normally present during measurement and the largest signals that could be present in any case. Most of the time, we don't really want to short the battery pack while we're testing. It's not normally a total use case for the battery. So the signals that we're trying to measure are much lower. And when we're deciding on equipment, we focus on what we're trying to measure first. For example, a battery pack that could output 100 amps, but if we're measuring open circuit voltage, we don't really need to be concerned that the DMM can handle 100 amps because ideally there'd be no current present in the circuit at all. But if we don't do anything to protect against that 100 amps and a random short happens and we get a failure, we've just set ourselves up for catastrophe. For good prevention and protection, we need to not only know what we're preventing, but how that failure happens. It may be a case where shorting two adjacent cells together doesn't really cause much concern, but if we short two whole modules together, we've got enough current to cause a fire. So we need to know that. Prevention is always our first priority. It's much easier to prevent a high current or voltage event from happening in the first place than it is to try to handle that situation later. So what can we do to help prevent failures? First off, use properly rated equipment. This goes without saying a little bit, but your instrument needs to be able to handle what you plan to measure, or it's going to be damaged and it'll need repair. Improperly rated fixtures, cables, and connectors will overheat. This can lead to fire or worse, shorts, because then insulation is compromised and it exposes the conductors inside, like you can see in the bottom left photo. When making connections, make sure all of your connections are clean. It's really easy for those tiny little strands and stranded wires to get bent and left hanging when you're using like a screw terminal. So use items like ferrules and collets to prevent that from happening. We see a lot of automated testing in battery manufacturing as well, and this often involves equipment that has to move to make connections to the battery pack. So if that equipment ends up out of alignment, it can touch down on incorrect locations and lead to a short. So make sure that all of your equipment is calibrated properly and is touching down where it's supposed to. And that goes for human operators as well. Make sure to put mechanisms in place to prevent any incorrect connections to the device. Another thing we see commonly implemented is switching to increase throughput, and this is great, but incorrect use can lead to damage, so make sure that all of your switches are properly rated and that you open any closed switch before you close the next one. And then finally, just maintain your system in general. Check your insulation for wear and tear and other damage that would prevent it from doing its job. Look for locations of strain, as this can also expose wires. We see this all the time, and there are pesky phone chargers and wired headphones that just from use and the strain of bending and going in your pocket, eventually that insulation does wear out and break, and now we've got exposed wires. Similar damage can happen on a test system, especially if you've got a lot of cables together and that test system is moving all the time. So it's much easier to replace a couple wires, add some ferrules to connections, than it is to build an entire new system if you have a fire. So we've done what we can to prevent a failure, and the hope is that that's enough and we never encounter an issue. But the world is not perfect and sometimes things happen. So now the next question we need to ask ourselves is, what do we do in the event that we do get some high current, like a short? How do we prevent damage to the system? The most common way to do this is to use a fuse. Traditional fuses use either a small wire or a small metal strip that melts with high current exposure, effectively opening the current path before anything can be damaged. There are also electronic fuses or e-fuses that open the circuit using FETs, and these have some potential for some faster operation and lower current operation as well. The protection is dependent on opening the circuit and preventing the current flow. So it's really important to note here that if you don't have any fuses in your system and a high current event happens, something else in your system will act as an unintentional fuse. Unless you know for a fact that what you are testing is shorting the battery pack and you've designed every single element of your system to handle that, there's going to be something in your circuit that can't handle hundreds of amps. And that component is going to burn out and open just like a fuse would. And that might not seem so terrible, but what if that component happens to be somewhere on the board of your DMM? You now have to have that DMM repaired. And what happens if it's not just one single component, but it's a number of components and a bunch of things end up damaged? It's just better to have the external fuse acting as the fuse. At this point, you may be thinking, doesn't my test equipment have fuses built in? And why can't I rely on that? The answer is yeah. Most equipment these days does have some protection mechanisms included in the design. But the fuses on the inputs of, say, your DMM are designed with the DMM's limits in mind. So if we have a DMM that's rated to 10 amps max, there will be a 10 amp fuse in the current inputs that will be rated to break and protect the DMM from a reasonable current above 10 amps. But it may not be prepared to safely break a current like 500 amps, or it may not break quickly enough to prevent other damage. This fuse may also be internal to the DMM, so even if the DMM successfully protects itself, you still end up having to send the DMM in for service to replace the fuse, which doesn't do anything to help us reduce costs and prevent line downs from damage. When testing devices that are capable of high outputs like EV battery packs, we really need to consider custom protection that's designed specifically to handle the current levels. Electrical arcs are also kind of unpredictable. They can jump across an open fuse. They can occur at the device rather than at the test equipment if the circuit allows for that. So we can't necessarily rely on the protection that your instrumentation has to protect everything else. Fuses are great tools to prevent high current flow, but we have to make sure that we're picking the right fuse. An improperly rated fuse isn't going to prevent the damage that we want it to. If it's overkill, it may not open at all, and that doesn't help us. Sometimes the fuse opens, but it doesn't open fast enough, so energy is still allowed to pass. We still get damage on the other side of that fuse. And then we have to remember that when the fuse opens, the voltage potential across that fuse increases because we now have an open circuit. And so it's possible to get an arc across the fuse, causing current flow even after the fuse is opened. When we're choosing fuses, there are two situations that we typically consider. The first is for short circuits or surges, which is when the current increases very quickly and we want to catch that current and stop it as quickly as possible. So these fuses tend to be very fast. The other option is an overload condition, which is where that current level is maintained for a period of time. So perhaps you've got a system where there's a bit of a current draw spike when the device first turns on, but you don't necessarily want to blow the fuse at that spike because you know that the current is going to decrease to a normal operating level. And so what you want is a fuse that takes more time to melt and open in the case that that current doesn't decrease. Depending on your test, you'll be protecting against kind of one or the other, but typically for battery testing, we're more concerned with that short circuit condition. When considering a fuse, the main specifications you'll be looking at include the rated current, which is the normal operating current for the circuit. You'll want to get as close to this value as you can, but you don't want to go below it because then your fuse could be opening during normal operation and then you have to keep replacing it. The rated voltage specification should be larger than the open circuit voltage across the fuses on opening. This is to prevent arcs from occurring once the fuse opens. The interrupt rating should be larger than the maximum short circuit current that could be present. So if you've got a battery pack that outputs 500 amps when shorted, you want your fuse to be able to interrupt more than 500 amps. If we had a fuse that interrupts less than 500 amps, the fuse could overheat and cause fires or explode when it tries to open, and that kind of defeats the purpose of having a fuse to protect from damage if your fuse ends up being the piece that causes damage. So then the final specification is the response time or the I squared T rating. The I squared T rating is used to represent how much energy is passing through the fuse as the fuse is melting and opening. Like I mentioned the two scenarios before, fuses that are considered fast-acting are best for short-circuit conditions, and time delay fuses or slow blow fuses are better for overloads because it takes much more energy over time to melt that filament and open. So a quick burst can pass through. When you're using a fuse, it should always be placed in line with the current path, not in parallel, as that defeats the purpose. You want the full current to have to pass through that fuse. The fuse should not be on the path to ground for a couple of reasons. One is that by putting the fuse after the voltmeter in this sample circuit we have, the current still has to run through everything before it gets to the fuse, and then the fuse opens, so you're still going to get damage on your DMM. It's better to place the fuse as close to the source as possible so that when it does open, you're protecting as much of the rest of the system as you can. Another reason you want to avoid fusing grounds is that in the case that a short circuit happens and your fuse opens, you've just disconnected the rest of your circuit from ground. And this can cause the rest of your circuit to still be at a live potential. So there's shock hazards for your operators if they're coming in trying to fix things. Or you could have the current could find an alternative path to ground, leading to more damage and more issues. And then if you really need help with selecting the right fuse for your test system, it's best to go straight to the experts and talk to a fuse manufacturer because they know the best about how their devices are working and what would help your system. Sometimes we do get asked if there's ways to protect your system against high currents without using fuses. Fuses are our preferred choice, but you can limit current by using resistors to dissipate power to keep current levels to reasonable limits. So say we had a battery pack and we want to measure the voltage on it, and that voltage should be about 800 volts. In our test system, we've got a switch that's only rated for 100 milliamps max. So if the circuit ended up shorted, we need to decide what value of resistor we need to keep the current at 100 milliamps or less. This is a very simple Ohm's law question, and we get an answer of 8 kiloohms. But we do need to consider the amount of power that that resistor will be dissipating. So when we calculate that, we get 80 watts. And it's kind of difficult to find a resistor at 8 kiloohms that can dissipate 80 watts. So what do we do? Well, we can increase the resistance, which will decrease the current, and that's fine because decreasing the current still keeps us within our limits for our switch. So say we move up to 800 kiloohms, our current is now 1 milliamp, and our power rating is 0.8 watts, which is perfectly reasonable to find. Seems simple, but now the next question is, does this affect our measurement? And the answer is yes. This is a voltage measurement, and so we do have to worry about loading errors in the DMM. In a perfect world, the DMM would be an infinite resistance and no current would flow, but real DMMs have finite resistance, so we're probably looking at an internal resistance of 10 mega ohms. And when we add in that limiting resistor, we formed a little bit of a voltage divider, and that's going to introduce errors into our voltage measurement. At 8 kiloohms, if we calculate the voltage across our DMM with that voltage divider circuit, we're only looking at 0.08% error, and that's negligible for the most part. But with that 800 kiloohm resistor, which we end up having to use because of the power requirements, we're looking at a 7% error on our measurement, which means that we're measuring 740 volts instead of 800. We could say, fine, we expect there to be a 7% error, and we could correct for that later once we take the data. And that might be sufficient for your application. But you have to be careful that resistors do have tolerances. Values can change over time. And so it can get challenging to quantify exactly what the error is that you're trying to correct for. And this is really why we recommend fuses instead, is because the process to do current limiting resistors can be hard to perfect, whereas a fuse should have minimal effect on the circuit at all. Switching gears here, I do want to talk about risks of high voltage exposure, and this comes most often in the form of common mode voltage. Generally, common mode voltage just means the voltage from each terminal, high or low, with respect to the internal reference to ground in the DMM. Modern DMMs do make differential measurements, which means that we're taking the difference between high and low, but each high and low is measuring with that internal reference to ground. And that's really useful for taking voltage measurements on circuits that have floating voltages, like battery packs. But it means that we need to be careful about how much we allow our terminals to float away from ground. Other sources of voltage, not just battery packs, can cause damage as well, such as charge buildup on items that are isolated, like a conveyor belt that your battery may be on. So let's take a look at common mode voltage when we're measuring cells within a pack. Say we've got a line of 200 cells that are connected in series, and each cell is 3 volts. To make my math easy, the voltage in the battery pack is floating because the potential difference in a battery is generated with respect to the electrodes. There's no reference to earth ground in the batteries unless we place one there. So the easy choice is just to stick it at the end of the pack where we consider it to be low potential end. When we get to cell 200, our DMM high terminal is at a potential of 600 volts with respect to earth, and our low terminal is with respect is 597 volts with respect to earth. But if our DMM has a common mode voltage rating of only 500 volts, we've just fried the low terminal of our DMM. So what do we do? Remember that batteries are floating voltages, and we are free to place our reference ground anywhere in the pack that we want. Therefore, we can take the method we were originally using, measuring each cell individually, and we can move the earth ground with the low terminal. So we're always measuring with respect to 0 volts, protecting the DMM from damage. The battery pack is not shorted, but rather just the potential with respect to earth ground at different points in the battery changes as we go along. We can see when we get to cell 200, the lower potential end of the battery is sitting at negative 597 volts, but that's okay because we just have a battery pack sitting there. There are other variations of this idea as well. For example, we could set the earth ground right in the center of the pack, which then splits our pack up into 2 sections, and we still get some common mode voltage. You can see on cell 200, we're sitting at 297 volts, and our high terminal at 300, but this is within the spec for our DMM. Nothing is damaged, and we are still okay. When dealing with common mode voltage, there are a couple things you want to be aware of. First, pay attention to ground loops from multiple grounding points. This is, can create an alternative circuit, shorting sections of the battery unintentionally. And so if you really want to split up the battery pack into multiple sections and avoid crosstalk or, shorting between them, it's best to use something like an isolation switch where it's truly separated. Also be aware that moving earth ground connections on the battery pack does change locations of hazardous voltage. So if we put our earth ground in the center of the pack, operators may assume that our low potential end of the pack is 0 volts and therefore safe to touch, but it's in the middle, which means that we're actually sitting at some negative several hundred volts, and that presents a shock hazard. If there is equipment in the system that's capable of building a static charge, like conveyor belts, consider using high-resistance bleed resistors. These allow the charge to dissipate without shorting everything, and ensure that the ground point on the battery pack does not drift too far from true earth ground. Lots of customers are using switching in their systems to increase test density, and multi-channel DMMs are a really easy way to do this, as the switching is contained within the DMM. There are several additional factors that we have to include when we consider switching. One is that the specifications of the switch cards may be a little bit different from the DMM. The common mode specifications for cards may not only be with respect from low to ground, but also between different channels as well. And this may mean that we need to consider high voltage cards. Switches also have maximum voltage and current specifications, as well as maximum power specifications. So any fuses or current protection needs to account for that in response time. And then lastly, you're working with many more measurement paths, and protection mechanisms like fuses will need to be placed on each unique path for the current to make sure that you don't have something that ends up bypassing your fuse completely. So to wrap everything up, remember that testing safety and protection is important both for protecting your operator and the system equipment. When setting up protection for your system, start with identifying the levels of signals that could be in your system and then what situations generate those signals. Practice good maintenance on your system to reduce any risks of shorts and electrical shock. And consider fuses to protect equipment from high current event, and consider grounding configurations to protect against high common mode voltage. If you're interested in more information, we have a number of application notes about battery testing. The information we cover here today can be found in our application note, Protecting Equipment During EV Battery Testing. We have application notes dedicated to specific battery testing procedures, including open circuit cell voltage, pack level open circuit voltage, and bus bar welding. And these contain some more specific information about the test methods that we're using. We also have 2 previous webinars as part of this series, making high-quality open circuit voltage measurements on battery cells and taking open circuit voltage measurements to the pack level. And both of these are available on demand. If you're interested in voltage measurements on batteries, I highly recommend taking a look at both of those. So with that, I want to say thank you all so much for attending. I hope you found it beneficial.